So we have been discussing on threading, and we have seen we have mainly discussed the concepts behind threading, like that each a process can have multiple threads of control, and then we have discussed a popular threads library called pthreads. That's not the only thread library. Like Windows has its own library, etc. But pthreads is the most popular library on Linux systems or Unix. That is what we have discussed. Now, today we will discuss some other aspects of threading. Okay, let's see. Yeah, okay, so this is what we have discussed, that what is a thread, and then we have discussed like multi-threading models, and then we have discussed the POSIX pthread library. So let's move ahead. Today we will discuss a few other aspects of threads. For example, thread scheduling, creation, cancellation, and so on. So let's talk first about thread scheduling. So we all understand what scheduling means now, that which process will exactly be allocated the CPU. Now the question of scheduling we have discussed in the context of processes, but we can ask the same question in the context of threads. So essentially, how will threads be scheduled? So we talked about two types of threads. Remember, we talked about user level threads and kernel level threads, and we talked about different mappings between these two. So one distinction between user level and kernel level threads is that how they are scheduled. So there are two fundamental scheduling paradigms: process contention scope and system contention scope. So I think even from the names, it is kind of intuitive what the difference is. Still, let's see. So in process contention scope, the situation is like this, that a particular process is given a time quantum, we know that, and say that process has several threads. So those threads in that process will compete with each other within that time quantum that has been assigned to this process. Okay, so this is usually done with user level threads, that suppose a particular process has created 5 threads, then the time quantum that will be given to that process by the scheduler, within that time quantum, that time quantum will be shared among these 5 threads. Right, so competition for the CPU takes place among threads belonging to the same process. This is also called unbound thread. And in contrast, the system contention scope is usually used for kernel level threads. And from the name you can understand, here all threads in the system are competing with each other for the processor. Right? This is also called bound thread. So usually this process contention scope is used for user level threads. That means all threads created by a user process is competing with each other for the CPU. And the system contention scope, that is primarily used among the kernel level threads. Right? So all those threads are competing with each other for the CPU. Now specifically about the pthread library that we discussed, that actually gives both these, that has kind of a mechanism to deal with which scope you are, having a thread. So it has these named constants or symbolic constants: pthread underscore scope underscore process. If a thread is going with this scope, then it means PCS, so process contention scope. And similarly, pthread scope system, if a thread has that scope, then it is running with the system contention scope. And pthread defines two functions: pthread attribute set scope and pthread attribute get scope. So again, intuitively it should be clear. Set scope, using set scope, you can actually set the scope of a process to one of those two, like PCS or SCS. And using get scope, you can know what is the current scope of a particular thread. However, Linux supports only pthread scope system, but not pthread scope process. So, like whatever threads are created in the whole system, they compete with each other across the system for the CPU. That is how Linux handles it. But some other operating systems might have pthread scope process. That is about thread scheduling. If you have any questions, feel free to write in the chat or write question that I can ask you to unmute and ask. So that is about thread scheduling. Now let us talk about thread creation. There are some subtle points which need to be discussed about thread creation. So we have discussed the system calls fork and exec. But when we discussed those, we only had processes. Now we have threads also. So we have understood that each process can have several threads. The fact that we are now talking about a multi-threaded environment, does it have any implication for system calls like fork and exec? As we'll see, they do. So suppose this is the question. Again, see here in this part of this lecture, we are not telling you what is correct or what is wrong. We are saying or we are discussing some of the points which have to be kept in mind by those people who have designed the kernel. Okay, so there is nothing specifically wrong or right here, but the design choices which the designers of the kernel had to make and what kind of choices did they make. That is what we are discussing here. So don't take this discussion as like what is right, what is wrong. One can think of like we will possibly at some points discuss what Linux does. But that does not mean that the other option would be wrong. Okay? Like in the previous slide, we discussed that Linux uses system contention scope. But that does not mean that you cannot design another kernel, another operating system, which uses process contention scope. So here also, we will ask several questions and then maybe say what Linux does, but that does not mean that doing anything else would be bad. Okay. So one question, important question is, suppose one thread in a process calls fork. So what is actually replicated? Does the new process duplicate all the threads in the original process? Or is the new process single threaded? Now there is no fixed one answer. There is no one fixed answer to this question. Like some Unix systems have two versions of fork. One which duplicates all threads in the calling process. Another version which duplicates only that thread which invoked fork. Okay, so that's about fork. However, in case of exec, there is usually a consensus. Like if one thread in a process calls exec, usually the program specified in the parameter to exec is typically used to replace the entire process. Right? So suppose your process has 5 threads, one of those threads called exec. Then not only that thread, but your whole process will be replaced by that program which you asked to be exec. So again, I mean, the designers of a kernel or an operating system have to keep these things in mind. Like what would be the semantics? If a thread calls fork, then what will happen? If a thread calls exec, then what will happen? So these questions need to be answered. Now, specifically in Linux, there are two system calls. Fork, we have discussed, the system call to create a new process. Also, Linux provides a system call called clone that is used to create a new thread. Again, we are not discussing the details of clone. Look it up. I'll leave it as a task. A set of parameters is passed to clone to indicate how much sharing is to take place between the parent and the child. So Yeah, I mean, do look up the clone system call and some details. Okay, so that is about thread creation. Like we discussed about what happens when a thread calls fork or exec, and we came to know about a new system call called clone. So at least in Linux, fork and clone two are provided to make this distinction. Like should the process be replicated or the thread? Okay, the next subtopic we will discuss is thread cancellation. So before going there, let me ask, can you think of any situation where a thread needs to be cancelled? That means, let's say your process created 5 threads. At some point of time, one of the threads need to be cancelled. That means needs to be terminated. Can you think of any practical situation where this might be needed? Okay, Deep has a good answer. Multiple consumers. Error in one should cancel all others. Okay. Any other ideas? Okay, another example which the next slide will say. Let's say you have a big array or a big database which you are searching for an item. Just to speed up the search, you are using 5 threads to search different parts of the array. If one thread has found the item being searched for, then actually the other search threads can be terminated, right? Because the item has been found. Okay, and Preet Kumar also has another possible suggestion, like maybe you have a multi-threaded application where different activities are going on. Now, maybe user has asked for a particular thing to be cancelled. Then let's say, I mean, okay, no, I mean that what Preet Kumar says reminds me. I'm not exactly sure what I'm going to say is correct, but still, let's say we are using a browser and we are downloading something. Sometimes we cancel the download, right? But that does not mean that the browser will shut down. So again, I'm not sure exactly how browsers are implemented today, but intuitively, the browser has multiple threads, and then that thread which was downloading your, which was, downloading some file on your behalf. If you have cancelled the download, then that thread should be stopped, whereas the other thread should still continue. Right? So that is the necessity of thread cancellation. Understand that we are not talking about process termination here. When we talked about process termination, things were easy, like your whole process needs to shut down. So you just call exit, you get done with it. Here we are not talking about that. We are telling that one part of your process needs to shut down or needs to cancel another part of your process. So maybe your process is running 5 threads. One of those threads or two of those threads need to be terminated. But the rest of the process should still continue running. Right? So that is what we are going to discuss now. So yeah, this is the example that I was telling. And it's good that some of you pointed out some other examples also. So essentially, there can be situations where you need to terminate a thread before it has completed. Now that thread which is to be cancelled is referred to as the target thread. There can be multiple target threads also, like in this search example. However, a particular thread that is to be terminated, we will use the term target thread for that. Now, there are some issues to keep in mind here. There are two types of thread cancellation, asynchronous and synchronous. But let's understand why the need for two. So in asynchronous cancellation, some other thread immediately terminates the target thread. This is immediate. However, this can lead to problems. For example, that thread, the target thread, may have dynamically allocated some resources. Or maybe it was in the midst of updating some shared data. And before it it had started updating the shared data, but before it could complete, it was terminated. Such situations can lead to problems like race conditions and others, like maybe a part of the updation happened and then the thread was cancelled. So then the system will go into an invalid state because let's say 5 items were to be uploaded, 5 data items were to be uploaded. 2 of them have been uploaded, 3 of them have not. So now the system is neither at the destination state, nor at the earlier state, right? So these things can happen if a thread is terminated all of a sudden. So then what is the other alternative? That is called deferred cancellation. This means that some other thread just indicates that a target thread is to be terminated. The termination is not done immediately. Some other thread just gives an indication that a target thread has to be terminated. The target thread itself periodically checks whether it should terminate. And if yes, then it clears up whatever it was doing, and then it terminates. So understand the difference between these two modes. In the one difference is clearly that the asynchronous cancellation is immediate, whereas deferred cancellation is not immediate. The other thing is, in the asynchronous cancellation, as if the control was with the other thread. It just told the target thread to shut down and the target thread shut down. But in the deferred cancellation, the target thread itself can take the decision when it wants to terminate. So it just sees that, okay, maybe another thread has asked for me to be terminated. It does whatever it needs to do. Maybe it was updating some shared data. Then it completes updating that shared data, and then it terminates itself. Okay. So this mechanism allows the target thread to terminate itself in an orderly fashion at a suitable point of time. Okay. Now, so again, there are these choices as to what should a particular thread library follow. Let's see what pthread follows. So pthread actually allows threads to choose one of several cancellation modes. Also, pthread allows a thread to disable or enable cancellation. Let's say a thread is doing something really important. Before starting that operation, a thread can say that the thread can disable cancellation. So as long as the thread has disabled cancellation, it cannot be cancelled by some other thread. Rather, the cancellation request remains pending so that the thread itself can later enable cancellation and respond to the request. In fact, the default behavior of pthreads library, in pthread library, the default behavior is deferred cancellation. Asynchronous cancellation is not recommended due to the reasons we just discussed. Okay. So cancellation occurs only when a thread reaches a cancellation point, and that can be how does a thread indicate that it has reached a cancellation point? By invoking a function called pthread test cancel. Okay, so if a particular thread, so see, you are writing the thread, you are writing the code of the thread. So you know what would be a safe instant or a safe part of the code where it is safe to terminate. At that point, you will call pthread test cancel. And if pthread test cancel indicates that yes, a cancellation request for this thread has been raised earlier, that means a cancellation request is pending, then a function known as a cleanup handler is invoked. Okay. So in that function, you can do some cleanup and then terminate in an orderly fashion. So again, understand that you are designing the code of the thread. So at certain points of time, when you know that you are doing something really important and the thread should not be terminated before completing this operation. While doing such operations, you can keep you can disable cancellation. Right? So other threads would not be able to cancel this thread immediately. Rather, if any cancellation request comes, it is kept pending. And when you know at a point of time, at a point of the code where maybe that important task which you are doing has been done, then you can enable cancellation. Also, you can also check if there is some pending cancellation request by some other thread. If yes, then you can do some cleanup and then terminate. Okay. Yeah. So pthread library gives this function called pthread cancel, and it takes as argument an ID of a thread. This is used to generate a cancellation request. So one thread can invoke pthread cancel on some other thread, specifying the TID of the target thread. However, invoking this function will not immediately cancel the target thread. Rather, it will only indicate a request to cancel the target thread. Now, the exact effect of calling pthread cancel depends on several factors, like how the target thread is set up to handle the request. If the target thread has disabled cancellation, then it might be deferred. So basically, this invokes something called a signal, which we will study in detail now. So at this point, any question? Okay, if not, then we will move ahead to discuss the topic signal handling. So before starting this topic, let me just tell you, signal handling is not exclusive to threads. We will understand what signals are, etc. But we will see that the discussion talks about processes. So actually, signals are a mechanism for signaling a thread or a process both. So signals can be talked about in the context of processes as well as in the context of threads. Right, so in the subsequent slides on signal handling, you will see that sometimes we talk about processes, sometimes we talk about threads. Don't get confused. Signals can be used with both. So now what is a signal? So signals are used in Unix or Linux systems to notify a process or a thread that a particular event has occurred. Okay. Again, note this is a very general definition. I mean, signals are not directly associated with termination or anything like that. Signals are a much general purpose mechanism, which is just used to notify a process or a thread that some event has occurred. Particular event has occurred. Now there are two types of signals, synchronous and asynchronous. Synchronous signals are generally generated by some invalid operation, such as illegal memory access or division by zero. Okay, so these signals are usually delivered to the same process that performed the operation that caused the signal. Okay, do you remember anything? By what we discussed about synchronous signals? Does it connect back to something that you have experienced earlier in labs while writing programs? So basically, if your program, if your process does something illegal, like illegal memory access or division by zero, usually the kernel will inform your process that something illegal has happened. The question I was asking was about segmentation fault. So typically it's an illegal memory access. Your program has done an illegal memory access. So the kernel will signal to your process that it has done something illegal. And there is a particular code which will be sent to you. Right. So different signals, I mean, see, there are signals for different purposes and they have different codes. Like if I remember correctly, SIG-SEGV is the signal corresponding to a segmentation fault, but I am not completely sure. I might have missed it. I mean, I might have forgotten the exact name of the signal. Let's just check once. Wait. Yeah. Okay. SIG-SEGV, also known as a segmentation violation or segmentation fault, is a signal used by Unix-based operating systems such as Linux. Yeah, fine. So yes, so like if so, I'm sure. I guess, yeah, I guess most of you have experienced segmentation faults at some point of time in your career. So essentially, your program has done something illegal. The kernel signals to your process that something wrong has happened, and I mean, also the kernel is helpful. So the kernel wants to tell your process that what went wrong. Therefore, it will send a particular signal called 670, and that should indicate to your process that some illegal memory access happened. Okay. So such synchronous signals are usually a result of something which your process itself has done. And basically, such synchronous signals are delivered to the same process that performed the operation which caused the signal. In contrast, there are something called asynchronous signals, which happen due to an external event. Right, so your process can get an asynchronous signal based on some other event, maybe which was done by some other process, or maybe even the user. Right? Let's say users terminating a process. I guess you all have seen or you all have tried out Control C. So maybe your C program has gone into an infinite loop. You have pressed Control C. Essentially, when you do that, the kernel understands that you have pressed Control C and sends a particular signal to the process that C program, that process. In the user wants you to stop. So what signal is sent when, say, a user presses Control C? Maybe can you look up the internet quickly and tell me? So when a user presses Control C, a specific signal is sent to the process which the user wants to stop. So the kernel sends a signal to a specific signal to this process which the user wants to stop. What is that signal? Yes, SIGINT, right? So int is for interrupt kind of thing. So SIGINT is sent to the process by the kernel, indicating that the user has interrupted you, that the user wants you to stop. Okay. So there are many different signals. Okay. There are many different signals, and each has a particular code, like say SIG-SEGV, SIGINT, which when it is given, it's like an error code. So when such a signal comes to your process can understand what went wrong or what kind of signal have I got. Now, what will happen when a signal comes to your process? That depends on several things. By default, some action is taken. Say, for example, if a SIG-SEGV comes to your process, the default action is to stop the process. Okay, so we know that if a segmentation fault happens, your program stops running. That is the default behavior if a SIG-SEGV comes. But in some cases, you might change this default behavior. We have a couple of slides a bit later to give some pointers there. You can change this default behavior. What happens when a particular signal is received? Okay. Okay. At this point, any question? I mean, there is one question which I expect from at least some of you. So, any questions at this point? So there is one question which, like, I would be happy if it comes to some of your minds. Does anyone have a question here? Okay, Nisarg is asking, these need to be implemented separately in hardware, right? Okay. Okay. I shall answer this question a bit later. But this is going towards that expected question. Anyone else has any question? Like what we are discussing about signals now, does it seem familiar kind of thing? Have we discussed such things earlier? Thread cancellation. Okay. Yeah, I mean, that is sure. That is what we have discussed just a few minutes back. Yes. I mean, thread cancellation is, I mean, yeah. So if one thread lodges a request for another thread to be cancelled, that thread will be given a signal, sure. But I'm not asking about today. Long back, have we discussed something which kind of seems familiar? Yes, Preet Kumar has the answer, or actually the question which I was looking for. So yeah, I mean, I expect some of you to come up with this question. And we discussed about interrupts. So now we are discussing about signals. They look similar. So are they the same? So the answer is there in the next slide. But before that, I would like you to take a guess. So do you think interrupts and signals are the same? If not, then what do you think is the difference? Okay, Jayant says not same. So Jayant, can you unmute yourself and say why not same? What do you think is the difference? So Jayant, can you unmute yourself and say?
So, yes, sir. Like I'm guessing signals are just they're not nothing to do with interruption. They're just signals with some values which we define that this value is to interrupt, this value is to stop, this value is to continue. I'm guessing that. So while modifying its behavior, we can modify instead of interrupting, we can modify the behavior of SIGINT and program it to do something else in the program.
Okay, let's see. And Deep, so Deep also, you can unmute yourself.
I mean, the interrupts we discussed before are sort of like they are known as synchronous interrupts. So in certain architectures, signals are implemented in terms of interrupts. So kernel sends an interrupt to the current running post process, and that's how it sends the signal. But it varies from architecture to architecture. So that's why I said it depends.
Okay, fine. Fine. Let me go to the next slide and okay. Yeah, the answer is that they're not the same. Let us go to the next slide and see some of the differences between signals and interrupts. And maybe that will also answer this question by Nisarg, which I have kept, so I have deferred that. So let's see. So signals and interrupts are not similar. What are the differences? So interrupts are used for communication between CPU and OS kernel, whereas signals are used for communication between OS kernel and other processes. So in general, interrupts, when you hear of interrupts, it's a more of a hardware flavor. Like interrupts are usually generated by some device. It may be the CPU or your memory management unit and so on. Though there are software interrupts too, but in general, like when you hear the word interrupt, there is a bit of a hardware flavor to it. Like some device is wanting to inform uh, something, so that's an interrupt. But a signal is software. Like the signal is initiated by one process and meant for some other process. Okay, and an interrupt is eventually managed by the CPU, which interrupts the current task and invokes the kernel provided interrupt service routine. So this is what we have discussed. There is something called an interrupt vector table, and there it is mentioned the starting address of the interrupt service routine. So when an interrupt comes, using the code, it can be figured out which interrupt service routine to run, and then, yeah, I mean, that is run. So essentially, it is managed by the CPU, which knows that if an interrupt comes, which part of the kernel or which ISR to execute. On the other hand, signals are eventually managed by the kernel, which delivers them to the target process or thread. Okay. So essentially, when you hear the word interrupt, it's usually to do with hardware, though there are software interrupts also. And when you hear the word signal, it is more of between one process and another. So signals are not implemented in hardware. They are essentially implemented in software itself. So one process sends a signal to another process or a thread. Right? So that is the difference between interrupts and signals. It is true what Deep said, but sometimes they may be used. I mean, sometimes the lower level implementation might be similar. Right? But in general, at the level we are talking about, or at the level we are discussing in, signals and interrupts are not the same. So like if a process tries to do a division by 0, this won't be like here the uh, process will get a signal, not an interrupt. Whereas interrupts are mainly meant for the CPU and usually sent by some device, etc. So that's the difference between signals and interrupts. Okay, so yeah, like so control C sends a signal SIGINT, so it's actually a signal, not an interrupt. Okay. Okay. Now there are lots of signals. Here, this is just a list of some popular ones. Like we discussed 6segv, like invalid memory reference. This is the signal which causes a segmentation fault. And SIGINT is for an interrupt. So control C has been pressed by the user, so that as the process gets SIGINT. There are other, for example, SIGKILL. This is an interesting, I mean, an important signal. If you want to actually shut down a process or a thread, then you can send SIGKILL. Okay. So how to send SIGKILL? Okay, I mean, some process will send it. So you can write a program which sends a signal to some other program, or I mean, you can write a program in which say one thread sends a signal to another. Also, as you will see, even using the shell, right, the shell that you use, the bash shell, you can send signals to other processes. So let's see, yeah. So okay, so now how is a signal processed? So as we discussed, it is generated by the occurrence of a particular event and is delivered to that process. Now, that process will handle this signal. How? There are two ways. One is, okay, so it's handled by a function called the signal handler function. Now, there are two possibilities. One is that a default handler is there. So till now, whatever codes you have written, right from your first year, you have not tried anything special about handling signals. So that means there is a default handler which runs, I mean, when a signal comes. And we know that when a 6segv comes to your process, the default handler simply terminates your program or terminates your process. That is the default action. This is the default handler. However, now that you are learning about signals, etc., you can actually define your own function, handler function. So then you can tell the kernel that, see, I have my own handler for this particular signal. That's a SIGINT. You can say that again, if someone presses Control C, default action would be to terminate that process. So that is the default handler. But you can say to the kernel early, I mean in advance, that hey, I have my own function to handle SIGINT. So even if someone presses Control C, I do not want this process to be terminated. Rather, I will do something special, which is there in my handler. So that you can do. So you can define your own signal handlers, which is used to override the default handler. Okay, just a minute. Yeah. So let's write a signal handler. It's simple. So you have to hash include these header files signal.h and unistd.h. And then this is the signal handler, this void sig handler. It takes as argument int signal number. So by the way, so these what we showed, these look like strings, but actually these are semantic identifiers to numbers. So essentially these are all int. So every signal has an integer number. Okay. So okay, so signal handler, of course, you can change this function name. You can change, but essentially this signal handler takes as argument an integer, which is the signal number, and then you can do what you want here. Like in this very simple program, if sig number is SIGINT, then you say printf received SIGINT. Okay, now this is important. As I said, you have to inform the kernel that you have written your own handler for certain interrupts. Sorry, for certain signals. Okay, you have to inform the kernel in advance that I have my own handler for this signal. This is what you do here, this line. So using this signal system call, you are registering that for SIGINT, my signal handler is this. Again, this is a function pointer. Okay, this is a function pointer of this function that you have written. So using this line, you are informing the kernel that if my process gets a SIGINT, do not run the default handler, rather run this function, which is my own handler for SIGINT. Okay. Then your process would not be terminated possibly just if someone presses Control C. Rather, it will, I mean, you will have the control about doing what to do, about deciding what to do. Okay. So that is how you can write your own signal handler. Okay. So that is about handling a signal. And how about the opposite side? How about sending the signal? There you can send a signal to another process or thread using two ways. One is you can, in your C code, you can use kill. Kill takes as argument the process to which the signal has to be sent and the signal number. Of course, I hope you understand that you cannot kill any process in the system. There are only certain processes which you will be allowed to kill. Maybe if they are created by you, only then. Otherwise, some malicious user will go on killing kernel processes or other users' processes. That cannot be allowed. So of course, the kernel will do these checks. That are you at all allowed to send a signal to that process? But this is how, using a C code, you can send a signal to a particular process, and you have to say which signal you want to send. Another option is via the shell itself. So you can actually send a signal like this, say kill, then minus, this is the argument to be given, command line argument, signal number, then the process ID. Okay. So this is what you can do. This is how you can send a signal. And the previous slide was about how you can handle the signal. Okay, one question remains, which I skip this. That how will signal, so suppose a signal has come to your process and that process has only a single thread, then things are simple. The signal is just delivered to the process. However, if you have a multi-threaded program and that program receives a signal, so multi-threaded process and that process has received a signal. So to which thread should the signal be delivered? Now there are several options. There is no one correct answer here. The signal can be delivered to every thread in the process or to some particular threads in the process. It might also be that while writing your program, you have written a particular thread to handle all signals. Right? So a particular thread is meant for handling all signals. So all these things are possible. And also, to which thread the signal has to be delivered often depends on the type of the signal. So a synchronous signal needs to be delivered to that thread which caused the event which generated the signal. Okay. However, an asynchronous signal such as SIGINT should be sent to all threads because clearly the user wants to shut down the whole process itself. So again, there are different options. We are not discussing which is correct, but depending on the situation, any one of these could be used. Okay. And yeah, so one thing is how to send signal to a specific thread. So just like for sending signal to a specific process, we had this kill function, kill, this one. To send a signal to a specific thread, we have pthread underscore kill. That takes as arguments the thread ID to which the signal has to be sent and the signal number. So signal number is essentially an int. So everywhere you will see that though they have these words like SIG, and SIGINT, they're actually just symbolic constants, and essentially like signal numbers are just integers. Okay. So that is about signals. Yeah, and if you want to know more about signals, go through these resources. There is a man page for signals, which you will in which you will get lots of details. Additionally, you can look up that resource, which is quite a good one. Okay. So we discussed about threads. I mean, some issues about threads like the cancellation, creation, and mainly we discussed questions today without the answers because these questions don't have any fixed answer. But just we discussed some of the questions which need to be decided by the people who are designing the OS. And finally, we discussed about signals. Okay. Okay, I'll take your questions, sir. Before that, let me just say, okay, this set of slides has a few other slides also, which I am not covering. That few other slides are for thread mutex. That means we discussed this earlier, that if you have multiple processes running or multiple threads running, which are doing something cooperative, that means trying to do a matrix multiplication like what your lab assignment has been given, then sometimes they may lead to undefined states like race conditions and other things. So if you, I mean that is specifically because you cannot depend on the scheduler. Like you cannot say that, oh, I had a process and I created two children. I want the children to run first and then my parent to run. You cannot ensure this, but that will depend on the scheduler. So that is why, because the ordering of which process will run first, which will run second, etc. When will a but okay, two reasons why these are difficult. One is that yes, you cannot make any assumptions about the ordering of the processes. Which process will run first, which process will run next. These are defined by the scheduler. You cannot control it. The other thing which you cannot control is that when your process or thread will be deallocated from the CPU. So suppose your thread or process is doing something important. It is updating a shared data structure. In between that updation, it is made to, I mean, it is deallocated to CPU and some other thread or process is allocated. So then that shared data structure remains in an inconsistent state because it was only partially modified. Right. So this is a problem. That is the problem that we will discuss starting the next class, which is called synchronization. Now we will discuss synchronization in the context of processes. However, there is also the need for thread synchronization. The next few slides give some brief discussion on thread synchronization. But since we have not discussed synchronization till now, I'm not going to cover them in class. So we will discuss synchronization in a lot of detail starting the next class. But these few slides, I think the next 3 or 4 slides are left for self-study. You won't possibly understand them right now, but once we discuss synchronization, then you should be able to understand the next few slides. Okay, so yeah, I'll stop there today. Now, yeah, Nisarg, you go ahead with your questions.
Yes, sir. So the first one is that when we actually register a signal handler using the signal function, uh, is it the kernel's duty to catch the signal and then execute it for the process, or is it like the process? It is the duty of the process to handle it, because I don't think the process can do it because it has its own execution flow, the instructions which are going on.
Okay, see, sure, but if your process gets a signal, then that function will be executed. That the kernel will, I mean, the kernel will give you, and the kernel will inform that the signal has happened. But you see, I mean, you cannot predict when the signal will come, right? So you cannot write code saying that check for the signal, and if the signal comes, to the, I mean, run sig handler function. You cannot write code like that because you don't know when the signal will come. So the fact that you have registered your function as a signal handler means that it will be arranged that if the signal, that particular signal comes to your process, then your signal handler function will run.
So the flow is like passed to handling the signal. There will be a place where the flow is passed to the kernel, the control is passed to the kernel does the needful and then returns the flow to the process. If like we have made some custom signal handler like this, where the process keeps going on.
Okay, see the signal. Okay, I'm not see the signal will be delivered. Sure, I mean, in order for your process to get a signal, most probably it will be delivered by the kernel, so the kernel has to run. And then let's say a signal has come to your process, but then your process itself contains the function which is meant to handle that signal. So what is the role of kernel here? The kernel will deliver the signal to your process, but how to handle that signal is you have defined it, right? The sig handler function.
Yes, sir. But a process is basically a set of instructions in execution, and nowhere does that like when we register a signal handler, okay, that's a step which was performed during the execution. But after that, all we have is a while one and sleep one loop going on.
Mm.
So where in this execution process does actually like I understand like okay a signal was delivered, but I was like thinking in the like in the hardware implementation side, like where does it so happen that okay now the process knows key this has come and I have to switch to that function.
Okay. So let me ask you, how is it decided which instruction will be executed next?
Using the program counter.
Exactly. So if it can be arranged that the program counter is indicating the start of that signal handler, then that should be enough. So the kernel decides, I mean the kernel, so remember that when processor is given to your process, the kernel decides what value to place in the program counter. Commonly it is based on, I mean, the saved program counter value. When your process was earlier like deallocated from the CPU due to your context switch, the kernel had saved the program counter value. That is the under normal circumstances, that is what is loaded back. But in case of this kind of a situation, the kernel will load a different value to the program counter. Because the kernel knows, right, that a signal handler is there and for this particular signal, that is the signal handler to run.
Yes, like that clears that out.
Okay, and Parth, okay, this, since Parth seems to have asked a question related to this, no, Parth, I mean, it's your signal handler. Your signal handler decides what to do after this. Like, I don't think the kernel decides that. Right. So if you write in your signal handler exit, then the process will exit. So once the kernel has given control to your signal handler, after that it is not the responsibility of the kernel to decide what to do. Any other question?
And sir, one small thing. So like say a division by zero or something occurs. So in this type of situations, it's a, like a two-step process, right? There's an interrupt from the CPU which informs the kernel that this has happened, and then the kernel will send a signal a signal to the process saying that, okay, this happened, and it sends a 6xv to the process. So it's like a two-step process.
I would not make it so simple because that's not a general statement I would like to make, that it's always a two-step process, that first an interrupt comes and then a signal. I would not like to make that kind of a, that would be too oversimplifying these things.
No, sir, not in general. I'm just saying sometimes like it may happen just for this specific
Yeah,
case.
okay. Sure, in some place, some places it can happen, like say a illegal memory access, then some hardware will detect that there's a illegal memory access, and then yeah, possibly there will be an interrupt and then a signal will be sent. But yeah, I would not like to generalize that statement.
All right, sir.
Fine then. Yeah, so let's end the class today here. Thanks everyone. We will continue next class.